In this video, we're going to be looking at the definitions of sine, cosine and tangent for any size of angle. Let's first of all recall the sine, cosine and tangent for a right-angled triangle. There's our triangle. We identify one angle and then label the sides. The side that's the longest side in the right-angled triangle and the one that is opposite the right angle is called the hypotenuse. And we write HYP, hype for short. The side that is opposite the angle is called the opposite side. Op for short. And this side, the side that is a part of the angle that runs alongside the angle, we call the adjacent side, or adj for short. The sine of the angle A is defined to be the opposite over the hypotenuse. The cosine of the angle A is defined to be the adjacent over the hypotenuse, and the tangent of the angle A is defined to be the opposite over the adjacent. But this is a right-angled triangle, and so the angle A is bound to be less than 90 degrees, but more than 0. In other words, it's an acute angle. So these, so far, are defined only for acute angles. What happens if we've got an angle that's bigger than 90? Or indeed, if we've got an angle that's less than 0? Well, that raises a question to begin with. Why, how can we have an angle that's less than 0? So first of all, let's just have a look at angles. I've got a set of axes there, and based upon the origin, let me draw roughly a unit circle. Circle of radius 1 unit, so that where it crosses these axes, x is 1, y is 1, x is minus 1, y is minus 1 there. Let's imagine a point P on this circle, and it moves round the circle in that direction. In other words, it moves round anti-clockwise. Then this is the angle that OP makes with OX, the x-axis. So there's an acute angle. When we get round to here, we've come right round there, and that gives us an obtuse angle, an angle between 90 and 180. Come round to here, and we've gone right the way around there, an angle that's greater than 180, but less than 270. And similarly into this quadrant. So that's positive is anti-clockwise. So we get positive angles if we go round in an anti-clockwise way. We draw it again. Same unit circle. And we think about our radius OP. What if we start to move it around this way? Then this is clockwise. And so this is a negative angle. So negative, we're going round clockwise. So of course we can go round from here to the y-axis, the negative part of the y-axis, and that's minus 90 degrees. If we go right the way round to the negative part of the x-axis, that's minus 180 degrees. Effectively the same as coming round to 180 degrees, coming round anti-clockwise. So that's how we can have any size of angle. The question is, can we put these two together? Can we bring together these definitions And these ideas about having angles which are greater than 90, both positive and negative. Well, let's take sine and have a look at that. So I'll draw the same diagram again. Put our point P on the circle, which is going to move around that way in an anti-clockwise direction. And here, mark this angle going round that way. Okay, sine is opposite over hypotenuse. Well, if I complete the right angle triangle, this would be the side that is opposite that angle. There is the right angle, so this is the hypotenuse. And because this here is a unit circle, the length of that is just 1. So the question is, how can I describe this line? Well, if I imagine I've got my eye here, and I'm looking in that direction, what do I see? I see that length as though it were projected onto the y-axis. So I'm looking that way, and I can see that length, which is OP, as though it were projected onto the y-axis. So perhaps a way of describing sine of, let me call this theta. A way of describing sine theta would be to say that it is equal to the projection of OP onto OY, the y-axis, divided by OP. And of course, OP is then just 1. How does it work with any angle? Well, think what happens as we go round. As we go round, as it rotates around, and you're still looking this way, then you've still got a projection. It goes down to a length of 0, and as we come back around here, we've still got a projection on this axis that we can see. So we've still got something that we can measure. When it gets round to here, of course, it's on the negative part of the y-axis, and so it's going to be negative. Well, let's have a look what that might mean in terms of a graph. What I've got here is a protractor, and the middle bit of this protractor rotates. Here, I've got a black line, which is a fixed horizontal line along there, and here I've got a red line, which is going to be my OP. This is the point P moving around in an anti-clockwise direction, marking out positive angles. And if it went that way round, it would be marking out negative angles. So they're going to start off together there, both pointing on 0, the angle 0. So let's recall that sine theta, the angle that OP, there's O, there's P, makes with the x-axis is defined to be the projection of OP onto OY divided by OP. But if I choose to make OP the measure, the unit, then sine theta is just the projection of OP onto OY. Now, let's have a look what that means in terms of a graph. So this is the axis, measuring, marking off the degrees. So I set that to 0. So the first point on the graph is there. Because as we look along there, what we see is nothing. We just see a point. So the length of OP, the projection of OP onto OY is 0. Now there, halfway round, 45 degrees. It's about that high. So let's mark it there. That's 45. This, 90. Let's move that around till we get to the top. Mark that across. That's roughly about there. When we start to go back down here, there we are, 135. The projection is along there, and taking that through, it's to there. When we get round to 180, again, as we look along there, we just see a point, no length. As we come down here to 145 there, or in fact 180 plus 45, which is 225, we get a point which is about there. And then as we come down to 270, about there. And as we come round here to 315 and through there, we're about there. And then when we come round to there, we're back to 0 again, or having been all the way round, 360. And if we join up those points, we get quite a nice, smooth curve. Out a bit with that one. If we think of this going back in this direction, what we can see is that we're going to get the same ideas developing. Here, let's just fill in the 90. It will be right down there, so it's there. And then at minus 180, right round there, it's there. And then at minus 270, going right the way around there, we're back up at the top again. And then at minus 360, having come all the way around, we're down there. And so again, we have a nice, smooth curve. Notice that this shape is exactly the same as that shape, and that we could keep on drawing it. This block repeats itself. It's periodic. It keeps repeating itself every 360 degrees. From there to there is 360, and similarly from here through here to here is also 360 degrees. So now we have a sine function, if you like, that we can think of as being defined by this graph. Covers any angle that we would want it to cover. We can keep on going for 720, 1,000 degrees that way, minus 1,000 that way. But this is always going to give us a well-defined function. What about something like the cosine curve? What about that one? Well, let's just have a look at that and see how we can make a similar graph for our cosine function. So I'll just stick that down again and quickly draw a set of axes. I'll not draw this one as accurately, but it should be enough for us to be able to see the results that we're wanting. So we'll mark off the divisions as we had before. 0, 90, 180, 270, 360, and then minus 90, minus 180, minus 270, and minus 360 there. Okay. The thing that we haven't done is made a definition. What do we mean by cos theta? Well, let's have a look. We want to do the same sort of thing as we did for sine. So that's the angle in there. The adjacent side will be this side, which is the projection of OP onto the x-axis this time. So O cos of the angle is the projection of OP onto OX, the x-axis, divided by OP. This is a unit circle, so OP is 1, so cos theta is the projection of OP onto OX. And now we need to look at that and see how that grows and varies as we rotate around. So we start with 0, and remember our eye is now looking down. And what we see is OP itself. So what we see is a point there, 1. We start to move this around. Let's go to 45, and we're looking down, so we see that bit there, which is less, which is smaller. So we see something about there. As we go round to 90, when we look straight down on this red line, all we see is a dot, and so the projection is 0. Let's go round, and now to 145, and now the projection is down onto the negative part of the x-axis, so this is negative now, down there. And at 180, well, we're now right round to sitting on top of OP again, of length minus 1. Start to come round again to 225, and again we get that projection back, so we're starting to be here, and then at 270, clearly again, we're going to come round to there, looking down that way. As we come round, the projection is again at 315, now a positive projection. So again, we've gone through there to there, and then at 360, we're back to 0 again, and so the projection is of length 1. So let's fill that in, join up the points, and again, we get a nice, smooth curve. And of course, the same curve is going to exist on this side. Let's just check. We're going to swing it round this way, and we can see that the projection is positive, but getting less until we get round to 90, when the length of the projection is 0. And so we're going to see this occurring round here, nice smooth curve up through there, up to there. Again, notice it's periodic. This lump of curve here is repeated there, and will be every 360 as we march backwards and forwards along this x-axis. So again, we've got a function that's well defined. We've got a nice curve, periodic, nice smooth curve. So that's our definition for cosine. Notice it's contained between +1 and -1. That was something that we didn't observe with sine, but that is also the case, that it is contained between +1 and -1, because this projection of OP onto OY can never be longer than OP itself, which is just 1. The other thing to notice is that the two curves are the same. If I just flip back, but displaced by 90 degrees. If we slide this sine curve back by 90 degrees, you can see it will be exactly the same as a cosine curve. What about tangent? Well, let's recall how we defined the tangent to begin with. It was the opposite over the adjacent. For sine, we replaced the opposite side by the projection of OP onto OY. And for cosine, we replaced the adjacent side as the projection of OP onto OX. What does that mean then for our definition? We draw our unit circle, take OP, moving around in that direction through an angle theta, and complete the right-angled triangle. This here is the opposite side. It's opposite to the angle that we're talking about. Tan theta equals, so the opposite side we have replaced by the projection of OP onto OY, divided by, now for a right-angled triangle it would be the adjacent side, and that adjacent side has been replaced by the projection of OP onto OX. Well, let's remember OY is the y-axis, OX is the x-axis. This again gives us a definition that's going to work as that radius vector runs around the circle like that in either direction. So again, it's going to give us a definition that will work for any size of angle. One of the things we can notice straight away about this is that it means that tan theta is, of course, sine theta divided by cos theta. And that gives us an identity which we need to learn and remember. Tan theta is sine theta divided by cos theta. But what does the graph of tangent look like? It's a little bit trickier to draw. Let's see if we can justify what we're going to get. Now, we're looking at tan theta, where theta is the angle between the x-axis and the y-axis. And we know that the tangent is defined to be the projection of OP on the y-axis divided by the projection of OP on the x-axis. So when we begin here at theta is 0, then we know that the projection onto the y-axis looking this way is 0, and onto the x-axis is 1. So we've got 0 divided by 1, which is 0. So we start there. For the angle 0, we start there. As we move round, when we come to 45 degrees, then the projections are equal. So let's just mark 45, and if the two projections are equal, then that must be 1. What happens as we come up towards 90? Well, the projection onto the y-axis is getting bigger and bigger, approaching 1. But the projection onto the x-axis is getting smaller and smaller and smaller, and it's that we are dividing by. So we're dividing something approaching 1 by something that is getting smaller and smaller and smaller. So our answer is getting bigger and bigger and bigger. It's becoming infinite. And we have a way of showing that on a graph. I've deliberately put in a dotted line, and our graph approaches that dotted line but does not cross it. And that's an asymptote. That's what we call an asymptote. What about the next bit of the graph up to 180 degrees? Well, as we tip over into this quadrant, then the projection onto the x-axis becomes negative, but is still very, very small. The projection onto the y-axis is still positive, still near 1. So we're dividing something that's positive and near 1 by something that's negative but very, very small. So the answer must be very, very big but negative. And so there's a bit of graph down there on the other side of the asymptote. And now we run this round to 180 degrees. And what happens then? Well, when we've got round to 180, the projection onto the x-axis is then of length 1, the same as OP, but the projection onto the y-axis is 0. So we've got 0 divided by 1 again, which gives us 0 at 180 degrees. So this comes up to there like that. Think about what's going to happen now as it comes around here. Let's draw one in. And we can see that the projections onto both axes are both negative. And a negative divided by a negative gives us a positive. You can also see that when we get here again, we've got exactly the same problems as we had when we got here. We're dividing by something very, very small into something that's around about 1. So again, our answer is going to be very, very big. And so again, we're going to get a climb like that. And as we move through this, it's the same as if we move through there. So again, we will start back down here, and the graph will climb, and then off up again there. What about back this way, when we've got negative angles? What's going to happen then? Well, we must have the same things occurring in terms of our asymptotes, and so we're going to have the same things occurring with the graph there, there, and so on. So again, notice we get a periodic function. That bit of graph is repeated again there. Every 360 degrees we get a periodic function. We get a repeat of this section of the graph. So that's our function tangent. And we can think of the function as being defined, if you like, by that particular graph.